Hello, this is Drew. I am a mathematics tutor here on Wyzant, and I tutor many different topics, but today we're going to be looking at linear algebra and I guess a little bit of real analysis thrown in there. So we're given a set V, we're given a function f, we're told to find the dimension of the kernel of f, find the dimension of the image of f, and to determine if f is a simple function. So the first two are a bit more straightforward. So let's just take a look, right? So we're given this set V, and there's this set V, which is this vector here in R3, such that x plus y minus z equals 0. We're given this function from R3 to R3, and we're told that V is the kernel of f. So that's an important thing right there. And we're given that one of the eigenvalues of f, because f is clearly a linear transformation, is 1. All right, so in terms of the kernel of f, we just have to look at how this is defined here. And we see here that this is all x, y, and z in R3 such that this is true, which means that we have to notice here that this is the equation of a plane. And that tells you there that the plane, the plane is mapped onto the 0 vector, which tells you furthermore that since the plane is two-dimensional, then that must mean, and then that entire plane is mapped onto the 0 vector, that tells you that the dimension of the kernel of f must be 2. And because of that, that must mean that this is a rank 1, which furthermore means that the dimension of the image of f must be 1. And when you think about it, it also makes sense, because if you're thinking about you know, 3D space basically, and you're imagining this plane, which kind of is like cocked kind of halfway through, it goes through the origin. And you're imagining this entire plane, or the space being transformed such that that entire plane gets mapped onto the 0 vector. You essentially have where all of that space is being mapped onto this line that is orthogonal to that, is normal to that plane, that kernel there. So it's all mapped onto this one line, which is one-dimensional, hence the image is one-dimensional. So that was the kind of easy part of this. Now the next part is to determine if this is a simple function. So we first have to define what a simple function is. So a simple function is defined as a function that can be represented like this, where f of x is the sum from k equals 1 to n of ak, and then there's this kind of one looking thing here, x. And this here, this ak, is just a sequence of numbers, you know, of numbers. Now this can be, you know, real numbers. In this case, you know, it would be a sequence of vectors. But in this case here, this little thing is our indicator function. Indicator function. And this is defined like this. This is defined as 1 if x is in AK, and 0 if x is not in AK. And AK, which is here, is defined as, oops, it's in this, let me rewrite that a little bit more neatly. An AK, that's not that much better, is in this set here. Now, it's going to be in a sigma algebra, but we can just, for sake of this in layman's terms, we can think of this as a partition of our space. So in this case, a partition of R3, right? So essentially what this is saying here, so and we have to notice here, this is going from 1 to n. So this is a finite This is a finite collection here. So in layman's terms, if a function is simple, you're basically asking, or if you want to determine if it's simple, you're basically asking, in this case, can f be represented as, a constant function on finitely many subsets covering, in this case, R3. So the idea is, can we come up with some finite partition? So where we have a finite number of subsets of R that cover R, where on those subsets we can define the function as a constant function. So you might get a sense of this idea already. Now, this is interesting that they included this information right here, right? That the eigenvalue, one of the eigenvalues is 1. This is a little bit of a red herring because, we know that the other two eigenvalues are 0 because of that kernel. But if you think about it, the eigenvalue being 1 along that, along the span of that eigenvector, that basically tells you that there's no scaling happening there. So if, for instance, if I had a value at, if I had some value at, 1 point or whatever, and I apply this transformation, that point isn't going anywhere. It's not going to move around anywhere if you're thinking about this in kind of space, and it'll be fixed there. And so you can assign that to be constant there. But there's a really interesting distinction. This can be a little misleading here because, fixed and constant are two different things, of course. So I think that they included that just to kind of throw people off. So what we have to think about is, can we partition, R3, can we partition it such that there are a finite number of subsets that cover all of R3, and within those subsets, this function has to be constant, and we can define the entire function that way. It's kind of intuitively clear that that's just not the case, because if you have some subset of R3 that has a measure that's not 0, then you're going to occupy a space that's larger than a point, if you will. And because this line it's not constant anywhere, actually, or rather, it's not constant over any interval. It's always increasing. In fact, this line is always going to have the form AA negative 2A if A is, in R. So this is never going to, this is always dependent on A for some value of A in R3, or in R. So this never has a constant anywhere over any interval. So because of that, this is not a simple function. Yeah, again, I think that this was a little bit more of like a conceptual thing of how you do that. In this case, you could probably prove it, which I won't do right now. But at the very least, I can kind of shed some of the intuition there for you. If you have any more questions, please let me know. Otherwise, good luck.